Hello and welcome to IEEE Soft Robotics podcast. In this podcast, we're going to interview researchers from both academia and industry about their work, thoughts, spectrum, and more beyond that. This is Marwa Edwini, and I hope you will find this podcast useful. If you would like to connect with us, simply send us, and we will be happy to hear from you. And here is my interview. Thanks.
Hello and welcome to IEEE Soft Robotics podcast. Hello, Professor Dieter. Thanks so much for joining us in the podcast. It's an honor to have you in the podcast.
Yeah, thank you so much for inviting me. I'm looking forward to it.
Thank you. So I would like to ask you first, how you would like to define yourself for the people maybe first time listening to you? How would you like to define yourself?
How would I like to define? First, just a brief background here. I'm Dieter Fox. I am faculty professor at the Allen School of Computer Science and Engineering at the University of Washington in Seattle. And I'm also leading the robotics research at NVIDIA. So I have two different positions, both of them very related to robotics. And I would specify my kind, so I'm a roboticist, but I would kind of define myself as a roboticist with very much kind of an artificial intelligence perspective, which means I am not focusing so much on, let's say, the hardware underneath robotics. I'm focusing more on, let's say, the computational aspects, which means I try to abstract away the specific hardware and try to focus on the general kind of algorithms and ideas that allow us to develop robots that exhibit intelligent behavior, which means robots that can perform complex tasks and also learn from experience, for example.
Wonderful. So before going to all these details, we ask a signature question about the childhood. How was your childhood was as a kid? Being interested, what interested you in science or technology? It wasn't clear for you. Childhood is so important. So how it was?
Yeah, so that's actually interesting that, for example, I cannot say that, from when I was a tiny little kid, I already built robots all over the place. That might be a bit disappointing. I was always interested in building stuff like with Lego, or back in Germany, we had what called Fischer technique, which means you can assemble certain things. I was building, let's say, cranes and how they would pick up objects and stuff like that. But it wasn't really the kind of robots that nowadays, of course, kids have access to, right? Also with already computers in them and stuff like that. So I was interested in these technical things, but also in school, science and math were my favorite topics. And my first robot actually that I then really had access to was when I started my PhD. So extremely late, because at college, so I studied computer science, and then I started the PhD where the idea was really focusing on artificial intelligence. And at the time, there was also Sebastian Thrun, a very famous roboticist, and Wolfram Burgard were both working with me there at the University of Bonn, back in Germany. And Sebastian, he convinced our PhD advisor, Professor Armin Kremers, to buy a robot. And at the time, this was a very big deal because you couldn't just go in a store and buy whatever, a robotics kit, right? So we had the robot shipped from the US from a small startup company. And Sebastian asked me if I was interested in also working with the robot kind of as a side project. And it sounded like fun, and I started working with it, and I got immediately hooked, I must admit. So this was kind of my little child experience, right? Where I felt like a little kid that gets a new toy, because suddenly you have this machine that's sitting there and you can control it with your computer, right? So it suddenly makes your programs come alive. And that was really an amazing experience. And yeah, I'm still with it.
Wonderful. So maybe I guess that's first system maybe you built on the first robot. So what kind of question pops up in your mind that when you first encounter the robot? What kind of question to intelligent behavior? Because we have also a question about embodied intelligence. What's really embodied intelligence? Is it the body or the brain, or both of them has to be evolved in a certain way? Either maybe to open-ended as we have in nature. So what kind of question, when you see this robot in what you do in computer science, what kind of question comes to you other than the later at this time? So what kind of questions? Yeah.
Yeah, so with respect to intelligent behavior, it's really this notion of how can we, let's say, take this stream of sensor data, right, that is in itself, of course, very impoverished as a raw signal, because it's really difficult to extract high-level information from it. And how can we extract information that is relevant for the robot and help it make decisions about how to move through the world, how to detect things that it wants to avoid, how to figure out how to get to a certain goal. And I think from my perspective, one of the key questions here is really this notion of finding internal representations for the robot that it can use to make these decisions and make and exhibit this smart behavior.
Mm-hmm. So maybe I'm just going to ask you in that case about maybe challenges or limitation, because you are really focusing on how we can design these algorithms. So going to the hardware, what you're trying to do, how do you see something still missing we have in robotics community when it comes to designing the hardware that can receive the capacity of what we want to do through the body, or in the robot in that case? So what could be
That's a good question. What is on the hardware side? I think when it comes to, for example, navigation or so, I think the hardware is pretty good. When you look at examples such as from Boston Dynamics or so, that they have extremely capable robots, right? Especially from the hardware perspective and the low-level control perspective. I think where the robots are still most impoverished from my perspective is with respect to the hand design, how they can interact with objects and with the world around them. So the kind of grippers we see in robotics are still kind of typically whatever they have, like 2-finger grippers. And if they have multiple fingers, then they're also very brittle. The design is often so that they are made of rigid parts, hard parts, right? And it's so different from, for example, human hands, which are so nicely, extremely articulated. The hands have these soft surfaces, which makes also, of course, interaction with objects much easier, because having these contacts with these rigid metallic parts, it uses a lot of slippage and things like that. So there's the question on how we can articulate these systems. And another key component from my perspective is really also on the sensing side, which means right now, most of the sensing we're using in these systems is either, of course, we use visual sensing, camera sensing to detect objects and things like that. But once we get close to the object, it's mostly about some very simple, either kind of force feedback we get through the grippers, but the sensing that we use, like on the contacts themselves, is still pretty impoverished. So there's some really exciting work going on developing finger touch sensors and things like that. But I think we're still not there where we have the rich kind of sensor that we have all along the skin of our hands, for example, right? And I think that would be something that could really push forward the robustness of how we interact with objects. That's
a very interesting point. I would like to stop here. So the part of sensing, even soft robotics, we have this issue that we don't know how to maybe still how the configuration of the sensor or what kind of material. So for you, when you try to doing it in the algorithmic side and you still need this data, what do you think maybe questions we have to ask so that we can solve this issue, or which direction we have to go for to get what you try to design the sensing in a robust way? That's first part. What kind of question or maybe direction we have to go for?
So if we have, so you mean once we have these sensors, then also like how can we really take advantage of those? And
yeah, and maybe because it's missing pieces here about the sensing, we're still not there yet in accuracy or robustness or reproducible sensing results. What direction we have to go for so that we can achieve what you try to aspire?
I think on the one hand side, of course, there's a lot of work to be done on just the engineering, mechanical engineering side of how to develop these hands, how to develop these sensors so that they also, I think, for example, cabling of how to get the data from the sensors to the computers, for example, is one of the big problems with these sensors in the articulated hands. On the compute side, of course, we then have to figure out how we can take advantage of all that sensor data, right? It's not that suddenly the sensor data itself is going to solve these problems. And that is where I think techniques similar also to what's been successful in computer vision and machine learning are going to be very, very useful, where the idea is that the robot needs to learn from experience, from interacting with objects in the real world, kind of what it feels like to touch them, and then learn representations from that.
Yeah, great. So maybe I'm going to ask you about maybe what's something you're doing in a research group, still maybe something very interesting if you can share with us what kind of research questions you have or challenges.
Yeah, so research challenges and questions. So again, I think one of the really big challenges is kind of high level symbolic reasoning about the world and evolving these kind of representations from raw sensor data. So for example, we're pretty good at, let's say, low-level control and teaching robots to perform low-level control tasks. So for example, if you look at all the examples from Boston Dynamics, it's pretty amazing what these robots can do. We are also pretty good at using, or if we have enough supervised training data, teaching robots, for example, about recognizing objects or reasoning about the environment in a semantic way. The same for tasks, like if you have a multi-step task, like how do you pick up an object, move it somewhere else, things like that. But somehow these low level and the high level are kind of disconnected, meaning that we often design them kind of independently of each other. And I think coming up with mechanisms that can just evolve these representations from the raw sensor data, that is one of the big open questions. And I hope that these new techniques such as deep learning, these deep neural networks can at least point us in the right direction for doing that, because they are very well suited for dealing with highly complex data.
So maybe a quick question about the expensive computation, for example. That's something we struggle sometimes in soft robotics or robotics, expensive computation. Sometimes we avoid modeling, and we have the question how we can close the gap between simulation to reality, what technique we can do that we can avoid this data and get this result. And so from your vision, what's something you think maybe we have to do so that we can close this gap?
Yeah, that's a good question. So I think there's, on the one hand side, I think in robotics, we tend to say that our robots need to be able to learn tasks and things like that just from whatever 5 demonstrations or something like that, right? But in other communities, if you look at computer vision, language processing, they have shown that an alternative approach, which is just if you have a lot of data, then even with rather weak supervision, you can learn actually extremely capable representations, right? And I think in robotics, one promising direction would be to look at, for example, tools like simulation, where we can now design simulation environments in which we can train these robots and provide them with a lot of training data that would be super expensive to do in the real world, right? So I think simulation can play a very, very important role here, because on the one hand side, it democratizes the research, because you don't need a super expensive robot in order to develop your algorithms. At the same time, it enables us to train robots in a safe way, and also to, for example, do benchmarking against other techniques.
Yeah, I think also related here, I think some people speak about how we can design this robot to be adaptable in a structured environment when it comes to simulation before leashing these robots to unknown environment. So what kind of design? Yeah,
that's a good question. So I guess you're hinting at that this kind of overfitting to the environment, right? The problem is if we train robots only in, let's say, these simulations, there's on the one hand side, there's a risk that there's still this, what the people call the sim to real transfer, which means this gap between what data looks like in the simulator versus what it will look like in the real world. And our robot might perform really well in the simulator, but it fails miserably when you try the same things in the real world. With respect to that, I think techniques are that we are looking at specifically is, for example, adding the right kind of randomization into the simulation so that it is representative of what you will see in the real world. There's been a lot of research on that topic. But what we are trying to do is also not just randomize, let's say, crazy amounts of noise, but we would like to randomize such that it is geared towards the real world, which means we're trying to collect real world data and use that data to refine how we randomize our simulator so that the simulators behave more and more like the real world. Let's say if we would only rely on simulation, is this notion that our robots will always only experience things that they will see in the simulator, which means which we as simulation designers came up with, right? And of course, as you're hinting at, there's always a risk that the real world it's so open-ended that there's many things that we cannot foresee, right? So how will our robots be able to deal with them? And I think really interesting directions for research there are things that are called curiosity-driven learning for robotics, or endowing robots with the notion of what's called intuitive physics, where the idea is, for example, with curiosity, how can we enable robots to go out in an unknown environment and then try to learn about this environment, new concepts, and interact with the environment and establish new concepts, even in a way that is not guided by a specific task. And if we develop these kind of algorithms, then our robots can also be curious in the real world, and that will hopefully help them to be much more robust and face unknown situations.
That's really interesting, Bart. I would like to ask you a question because I think that's something maybe related. So when you have this design for the brain and the design of the body in that case, and assuming we go into open-ended scenario for that case, which one do you think we have to invest more in, the brain or in the body to adapt to the brain? Or how do you see the adaptation if we can redundancy, assuming that we have to go for redundancy situation? Which one you have to weigh for more, the morphology or the shape of the robot or the brain in that case?
That's such a good question. Yeah, the kind of where should we put more effort, the brain or the body? As an AI researchers, I personally choose to work more, let's say, on the brain side, on the compute side. And the reason is also, if you look at examples where people, for example, have remote controlled a robot, right, with the current hardware. So for example, at the NVIDIA lab, we did a project that's called Dex Pilot, where we took a robot hand, it's an Allegro hand, which is a robot hand with 4 fingers. And we had a person in a motion capture system that we built remotely control that robot. And through that remote control, actually, we were able to do pretty sophisticated actions with this manipulator. So for example, it was even able to, there was a wallet on the table and they were able to open the wallet and pull out a $10 bill, right? Or open like sophisticated small cabinets and things like that. So that tells me that the hardware is at least far more capable than what we with our autonomous algorithms are getting out of them right now. So I think there is a huge amount of work still to be done on the, let's say, the pure intelligence of these systems. Again, at the same time, of course, we need to develop also the hardware further to improve our robots. But for me, one of the exciting direction is really on the brain side.
That's interesting. So maybe also because I think maybe you'll ask about the Moore's law, for example, that case, and the control we have, or the architecture we have. From your perspective, because we now see that Moore's law is not really valid anymore. So how do you see the vision of the computation power? If we wanted to simulate something, our brain. So how do you envision the architecture looks like in that case?
I think as we see right now, for example, with a lot of the work going on in the deep learning community, right, that with these neural networks, which are not like really good simulations of the brain or so, right, but with this highly parallelized computation, we can actually build systems that can perform extremely complex computations, like on the perception, learning, and decision making side, that operate also in real time, right? And of course, that was one of the motivations why I also was joined NVIDIA, because with their GPUs, they're kind of the prime compute environments for enabling this kind of processing.
Mm-hmm. Great. Yeah. So maybe we can ask a few questions from the audience, because they have lots of questions, but we will go for a few. The first question is, what's the future of SLAM, and is it solved, or can we still improve compared to currently existing solution?
SLAM, maybe first I should, as context, SLAM stands for simultaneous localization and mapping. And the idea of SLAM is, how can a robot, for example, let's say a robot has a laser scanner or a camera on board, and it moves around. And as it's moving around, it's trying to build a model of the environment. And some of the key problems in SLAM are that it's becoming less and less certain about its position, and it needs to bring all this data into a consistent representation, spatially consistent representation. Now the question is SLAM solved? It's a very loaded question, and there's many people who argue about that. I think, from my perspective, SLAM is actually just a small part of the real question, which is about representations of environments. So with SLAM, people often connect this focus on just getting the locations of everything right, estimating exactly where landmarks are or where certain objects are. And I think what's going to be much more important is a more semantic representation of the environment. So for example, we humans, right, we clearly don't have a very accurate 3D model of our house in our mind, right, when we're navigating around. Or if you go into an office building and someone tells you, okay, the office is on the 3rd floor, and you go down the hallway on the right, something like that, we don't need a very accurate 3D model of this environment, right? So our understanding of this environment is much more at a semantic understanding of objects, of certain pathways that we follow. And I think that is something that we need to endow our robots with as well. So again, I think SLAM itself isn't solved yet. There's still many open questions in the SLAM work itself. But if you broaden the scope of SLAM, then it's just a wide open research area.
Great, thank you for sharing that. And the next question is, how much of a role do you see ML and machine learning methods playing in SLAM in the future? If you have any other comments you would like to say about the question,
Oh, the role of machine learning in SLAM. Well, on the one hand side, if we're talking about these extensions to, let's say, more semantic understandings of the world, then clearly machine learning can help a lot with extracting these semantic information from the sensor data, like computer vision techniques, right, that can then enable the robot to reason about objects in the world. Interestingly, initially people thought that because SLAM itself is such a geometric process, geometric reasoning process, also related to structure from motion and other techniques, that deep learning can't really help with that, for instance. But we've seen a lot of progress by incorporating deep learning processes into these SLAM techniques. So I think even on the basic SLAM technology, there's still a lot of work that can be done by combining it and incorporating deep learning techniques into that. And then I think they will become even more robust than they are right now. And we've seen some really exciting examples for that, I think, over the last years.
Right. And other question asking about what is missing problem in robotics that you are tackling? I think we maybe cover something about that, but if you have other comments, and one that isn't completely solved or doesn't have high quality real world implementation.
Our problem right now that is, well, I think, so on the one hand side, we do a lot of work, for example, in, let's say, object manipulation, right? A lot of that is focused, of course, on rigid objects. You can see a lot of work that's also focusing on things like deformable objects such as cloth or ropes. But what I find really fascinating is all this, what you might call stuff out there that is not rigid objects, but that is something that is just really hard to model. So for example, think about a kitchen environment, right? Like how do you represent salad, vegetables? How do you represent operations such as chopping an onion? Like, what's the representation of this onion? Is it this one round thing, or is it then these little dices and cubes that you're generating by slicing it? Imagine you want to have a robot mix dough, bake a cake. So how does it reason about flour and water and how these things mix together? And interestingly, I think we humans have a pretty good intuitive understanding of these things, right? Because otherwise we couldn't kind of operate so well at them. For example, like slicing an onion, right? But at the same time, this understanding that we have is not just perfect physical understanding, right? It's just what I said, this intuitive notion that we get from experience over time. And I don't think we have a good way for endowing our robots for that. There's research going on in that direction, but I think it still has a long way to go. So, which means representations of things that we can't just model that easily.
Mm-hmm. That's a very interesting point. Maybe a quick question here about, you mentioned two things I think very important about, maybe, yeah, the first thing like closing or dicing onion or soft object, the modeling part, which one do you have to weigh so that you can represent this situation? Do you think the modeling, maybe lack of modeling and intuition, the part of intuition is interesting, how you can represent the intuition or gut feeling, all this kind of complexity in what we have, how we can abstract them?
Yeah, that's a good question. If I only knew how we can go about it. I personally, and there's of course I'm sure it's controversial. I personally believe that these new techniques coming, let's say, from the deep learning community are gonna be very powerful in that area. Where the idea is, rather than me as the engineer of these algorithms, for example, imposing a very clear structure onto how the robot should think about the world, which is what we're doing right now. Often, right, we say there's an object and the object has a 3D model and it needs to reason about that 3D model of the object. I think we need to look at ways of just learning, letting these representations evolve from the data. And in deep learning, now there are several techniques that can be used where you just collect data in the environment and you learn representations, for example, that are able, for instance, to predict, let's say, the future, which means I'm looking at the data that I have up to time t, and then I train a system that can predict what's going to happen conditioned on my actions in the time t+1, t+2, and in the future. And the nice thing is that we can learn these, what's called predictive representations. We can learn them in a self-supervised way, which means the robot can use its own experience to learn such representations. And the hope is that by learning such representations, it can also use them then to learn control tasks and to understand the environment better than if we as designers would just decide on what the representation should look like.
That's also a good point. These days, machine algorithms are used in the most of research robotic algorithm. Is the usage of machine learning becoming excessive? Is machine learning is really providing enough benefits with respect to its usage of level, or it's hindering the research progress?
Yeah, that's a good question. So whether we're overdoing it with the machine learning, right? And I think it's interesting. So compared to other communities like the computer vision community, it turns out that the robotics community has actually been pretty hesitant of adopting machine learning and deep learning as one of their key tools. But when you now go to the conferences, I think the number one keywords are all related to machine learning, deep learning. And I think, first of all, I don't see machine learning as something, it's an either or, right? You do machine learning or you don't do machine learning. I think machine learning is one thing that we should have in our toolbox, and we should apply it to the problems we're trying to solve. I believe we are still just scratching at the surface of what you can do with machine learning, right? Some people, I think, commit the mistake that they say, oh, right now machine learning has all these limitations and therefore it will never be able to solve really hard problems. But of course, machine learning itself, the tools themselves keep on developing and evolving and get better and better. So I believe that we're going to see even more capable machine learning tools. And I think they're going to be just extremely important, because we just can't manually design the whole world around the robot and the reasoning processes for the robot. I think they have to be just learned in a data-driven way, and the robot needs to be able to just constantly learn as it's operating in the environment.
Great. So the other question also here, when is Nevada Isaac is, I hope I say it right, going to be full-fledged released? Will it support Ros and Ubuntu?
Oh yeah, that's a good question. So fully fledged, what does fully fledged mean? Of course, right? So first of all, Isaac SDK is an SDK that's designed for robotics, specifically with an eye towards taking full advantage of, let's say, GPU processing and GPU parallel computation. So it has specifically towards enabling deep learning, incorporating simulation into the learning processes, and also enabling high-speed communication. And Isaac Sim is a tool for kind of developing simulation tools specifically for robotics, such that they have a high physical realism, which means they really model well the physical context between the robots and the environment, how objects behave in the physical world. And also, how can we develop environments in which we can train our robots, right? And how can we make them look photorealistic? So we can now develop simulate environments that look virtually like the real world, right? So this is kind of the tools that Isaac SDK and Sim are developing. And I don't think at any point that we say we're done with that, right? It's really about continuously evolving them and making them accessible to the robotics, both research and industrial community, so that they can use them. So there was one question about Ros interfaces and Ubuntu. It turns out that both Sim and SDK, they do support Ros and Ubuntu already. So the simulation, I think currently the release has a Ros interface, and they're currently developing one for Ros 2. And the SDK has a specific Ros bridge so that you can connect your Ros tools to the SDK. So the idea is actually to make this interoperable as much as possible.
Right.
And
there's also a question
just maybe one additional point, I also want to mention that many of the tools that are being built are also accessible within the Ros community. So many of the tools that are highly specialized, again, for high-speed GPU perception and things like that, they're also made accessible as part of the Ros community.
Great. So the next question was so much same to real training. How can you account for things like serendipity when models are built in synthetic world? Although we are designing environment as we see them, is it possible that we are missing out sensation that other intelligence can identify in the world?
Yeah, I think that's a good question. Um, it's it's very much related to what we discussed earlier on, right? Where the idea is that if we only train our robot in these environments that we as engineers, let's say, develop for them, then we're not going to be able to model all surprises that the real world would have for our robots, right? And that is why I think it's important that we look also at what you might call these meta algorithms, like curiosity or so, right? Where curiosity is not just a specific behavior, but it's kind of an approach of how you operate in the world and how you view certain tasks that you are solving, right? And I hope that these notions, if we can develop them, that they will then make it possible for robots to succeed, even if the real world holds many surprises open for them.
Mm-hmm.
And I think it's also related to this notion of lifelong learning, right? So for example, if we ever want to have a robot in our home or in the kitchen helping us with certain tasks, I would never expect to be able to buy a robot and from day one on, it's going to be perfect in my home, right? But what I would like to have is a robot that comes in with basic capabilities, like it should be able to recognize whatever coffee mugs and things like that. But it should also have the learning capabilities such that it can become an expert in my house. So I don't need my robot to be an expert in your house. I want it to be really good in mine, right? So they need to be able to keep on learning. And these techniques, maybe those we can develop in simulation because we don't know exactly yet how to do that even.
Mm-hmm. So next question. I have dreamed from the audience, I have dreamed of building robots since I was a child. As a software developer with 15 years of experience, how likely is it that I can find a company willing to take a chance on someone wanting to join the company in any capacity, just to get a chance to learn and one day build robot myself? Perhaps a transition from enterprise software to robotics. It's like a shift, yeah.
That's a good question. I mean, many companies are with robotics becoming more and more relevant for real industrial applications, right? And I count, for example, also self-driving cars into this robotics class of applications. So with more and more of these domains becoming really viable businesses, more and more companies are hiring in that area, right? And of course, there's a huge need for software engineers and software developers. So on the one hand side, if you're in a larger company, often there might be moves you could do to a group where you're attaching yourself to an existing robotics team, for example, and offer your expertise. In general, I think many of these companies are, of course, looking for people that have some experience already in robotics. For that, I would recommend also take some of these online courses. There are many courses online available nowadays that people can take for understanding, for example, machine learning, robotics. Get one of these robot kits that are actually nowadays also not that expensive anymore, and play around with them, because I think for robotics, there's nothing more important than actually doing it on the robot. I think it's really hard to learn all the complexities of robotics in simulation. So even these cheap kits can already teach you a lot about robotics.
Yeah. So the next question is what is your outlook on cobots or cooperative robots? Do you have any internship that accept international EE student? And what's your view on robots and elderly or sick care?
Oh, interesting. Yeah, so with respect to internships, yeah, both at the university Washington in my research lab there, and in video research we frequently have international interns and also visitors from other universities that spend, for example, three months to half a year with us and do research in the lab with us. So that's one opportunity to apply to these. In some places, of course, we do expect that there's some prior experience and connection already to the research projects, because otherwise there might be too long of a ramp-up time. And then there was a question, what I think about robotics for, was it elderly?
And sure, yeah.
I must say, I actually think this is the by far most exciting use cases for robotics, and I think some of the most viable use cases. So I don't think for example, the general household robot that's gonna clean your kitchen and cook your meal is gonna be the first viable robot in the home beyond, let's say, vacuuming. I think the real first relevant use cases will be in the healthcare sector, will be in the elder care sector, and helping people with disabilities. So I think that is an extremely positive use case, because it has a really good impact on society, can help us with the problem we have right now. So there are just not enough people to help people to take care of elderly people in their home. So right now they often have to go, for example, to a nursing home. But if we had robots that can help them even with some mundane tasks like bringing them the food and things like that, that could already be a big plus. So I'm extremely positive about these use cases, and I think those are the most exciting ones that we should work towards.
Right. So there's also another question the audience asked us here about. I'm a recent undergraduate in engineering field. What should I do to get involved in industrial robotics research? Where do you see the future in robotics innovation heading? I think that's also, yeah, a good question.
Yeah, I think similar to the previous point, right? I would suggest take courses in these areas, right? And there are, of course, core, let's say, robotics courses. Again, I believe computer vision courses, deep learning courses are going to be very relevant. And they are exceptionally high quality. And nowadays, actually, even what I do online on YouTube, many lectures are online, right? Even I still often take a look at them if I want to learn something about a specific technique or so, right? Just keep on learning. And when it comes to which area of robotics, I think all these areas are super exciting. So there's still huge amount of work to be done on the hardware side, as we said, but also, of course, again, the brain, the computing side, perception, control side, learning of these robots is going to be very, very important moving forward. And one topic explicitly that I have mentioned is also, I think, human-robot interaction is going to be a really, really important area. Like, how can we get these robots to interact with people in a natural way? How can we get them to understand humans around them? And what are the interfaces even, right? Do you have, whatever, a touch screen? Do you need to program these robots? Or there's also hopefully work towards, can you just talk to them? Can you just tell them what to do? That would be ideal. It's not easy, but I think there's so many really interesting research questions that we still need to address.
Maybe a quick question here. For your experience, do you have something in your explanation when you try to model something or explain something, when it deployed on the robots was surprising and counterintuitive, or having emergent behavior? Do you have any something like that happen, wasn't expected or surprising the result, or counterintuitive to what you already thought about?
Yeah, there was, surprise. There was actually pretty early on one example was we developed a robot, a museum tour guide robot, right? Where we had a robot navigation system, and we wanted to highlight that we can get this robot to navigate through populated environments. So, and we deployed one robot in a technical museum in Bonn and one in Washington, D.C. And one of my tasks was actually what's called collision avoidance, which means your robot gets a goal position sent to it by a planner, let's say, which means something like, okay, get to a location 3 meters ahead. And the robot is using its sensor data, like a laser scanner or ultrasound sensors, in order to detect where obstacles are around it, and it tries to move around them. So, and I spent quite some time on tuning that system, and we tested it a lot in the university, in the research lab, and it was pretty good at detecting obstacles and then smoothly moving around them and getting to the goal locations. And when we tested it also, we would stand in front of the robot and it would nicely move around us. But then when we deployed it in the museum, it was so crowded sometimes that people, and they just wanted to see how the robot reacts, people would stand in front of the robot and would look at it, and the robot would constantly try to move around them. So which means it would rotate away and try to get there. And then there was another person standing there, and it was totally confusing to the people because they didn't know what the robot wanted to do, because it was constantly rotating and turning around and things like that. And in the end, the solution to this problem was, when there was a person in front of the robot should just stop. And then we had a loudspeaker system on the robot, and it would just say, could you please stay behind me, or I need to get through. So this was an example where if you design something in your research lab, you often just don't see where the real problems are. And that's why I would encourage people to always try their stuff in the real world, because that's where you learn what the real problems are, right? And in that case, we just didn't anticipate how, let's say, people would behave around the robot, right? And then how we would deal with this.
Absolutely, I agree with that. Yeah. So we have a question from 15 years old, and he has a lot of questions for you. So first he asks you, what are your thoughts in using human imitation learning, AI, to full movement and behavior of future robots? And he said that I live in the UK and I'm 15 years old and very interested in robotics. And he asks, what courses do you recommend? I think you covered that. I can take at university to start my own robotics company. So, and I'm not very skilled in programming. However, I think advanced AI is what modern robotics lack in order for them to be truly practical. He asks you if it's worth me taking a course on AI at university to build better robots, or should I focus more in mechanical or electronic engineering? And what do you think is the next biggest step needed for robots in order for us to see robotics revolution? What do you think? Sorry, it's a long question. So what do you think about universal platform and for robotics and electronic communication, so robots can work together? And which robotics? Yeah, it's a long question. Maybe
and it's related, I guess, to some of the questions, but where, again, I think AI, of course, or let's say AI-related techniques are very important for designing robots or developing robots, right, that can just learn to deal with the complexity of the real world. We cannot just manually program these robots to do that. So having good background in AI is certainly a plus, but at the same time, it also depends on what your preferences are, right? There are many open, exciting questions with respect to mechanical designs. As I mentioned, for example, on manipulators, hands for robots is just a really open space. So, and then it's not either or, right? It's this co-development of these techniques. So for example, if you have these good hands, you suddenly need new algorithms for controlling them and for taking advantage of the new capabilities of these hands. So even if as an AI researcher, you should know something about the mechanical side, and as a mechanical engineer, knowing something about the artificial intelligence algorithms and machine learning algorithms can be extremely beneficial. So I don't see this really as an either or question here.
Yeah, great. So it goes and I have a few questions. The first one, what's something for you still hard to understand when it comes to work? Something still hard for you to understand?
Well, for me, again, the really, really big question is how we can get to higher level reasoning and understanding about tasks and environments from experiences in the real world and raw sensor data. Like, how can we come up with these mechanisms that take this continuous stream of high dimensional data and somehow compress it into something that doesn't have to be explicit symbols, but it resembles, let's say, what we often call these symbols. And that is also related then to, for example, language, right? Where linguistics are looking at how language evolves, how symbols evolve, compositionality of language. I think all of these things are connected to each other. And I believe we still have a long way to go until we really crack that nut.
Thank you for that. And we have a question about intellectual inclusiveness in academia. So how do you see the intellectual inclusivity when it comes to different approaches, different ideas? We have few funding and there's a competition and also publication pressure at the same time. And some people complain about this kind of pressure. You wanted to answer these big questions and at the same time you have the pressure to do incremental work sometimes as you're going to risk ideas.
Yeah, that's a good question. And yeah, there might be a tendency sometimes in communities to become too much focused on a certain area, right? Because everybody gets excited about a new technique or something like that, as for example, like deep learning right now, and other techniques get too little exposure, or sometimes even reviewers might just say, oh, no, that stuff could never work. I'm not going to accept these kind of papers. So I think all we can do is, as advisors, make sure that our students stay open-minded, right? I think it's important that we try out different techniques, different approaches, different mindset for solving problems, and that's going to be crucial. So we need to make sure that that is really ingrained in the reviewing process, be it for funding, be it for at conferences as well, because of course getting your papers published is important. And for individuals, if you're convinced about your technique, I encourage you to stick with it and see how you can make it work and convince others. I think the best way to convince others that your work is really good is by solving problems that these other people care about but don't know how to solve, right? Like showing that you're competitive. That was one of the main problems, for example, of, as we know, deep learning in the computer vision community, where the vision community was extremely hesitant to accept deep learning as an interesting or viable technique until the deep learning technique suddenly got the best results on some of the key benchmarks. And then suddenly this was an eye-opener. And now, of course, it's pervasive in that community, right? So I would say perseverance is important, right? Try to keep on pushing if you're convinced. At the same time, you yourself also stay open-minded, right? Don't just dismiss other people's work or other people's thinking. And always kind of question your own approach, right? Like think about, so is that really the right way of doing this? And when you see another paper that comes up with a different technique, think about it. So what are the advantages of that technique? And could I either incorporate that into my approach, or should I even, in the extreme case, should I just adopt that and keep on moving with this direction, right? So flexibility is important.
That's a very good point. Yeah. And do you think ego is important for you?
Could you repeat that?
Do you think ego is important for you when it comes to expressing your ideas?
Oh, ego.
Yeah.
I don't know. I don't think ego is any more important in research than in other domains, which means I don't think it's actually really important, right? I think for a successful research career, it's much more important what I just mentioned, these qualities of being open-minded, being curious, right? Interested in new things. Also, I think what's actually important on research is being collaborative, right? Willingness and also actually the desire to work with others, because often problems are way too big for you to individually solve. I think those are properties that are much more important than having a big ego, right? We know many people that have a huge ego and they're not doing great stuff. And we know people that have maybe a small ego and they're making the greatest contributions. So the answer is, I don't think it's particular.
Thank you for sharing that. And what could be the most important quality you have gained when you work in academia? What could be one important quality you have to maintain?
Yeah, the things that I just mentioned, right? Like really kind of being willing to learn new things and being open-minded.
Okay, and then is there any book inspired you would like to share? Any book inspired you?
Oh, a book that inspired. Yeah, I must. Yeah, there is actually the book that I think had the biggest impact, if you think about it on, or if I think about it also on my career and my life, was actually maybe you heard of this Gödel, Escher, Bach by Douglas Hofstadter.
I don't know this book, no.
See, there you go. You should read. So this is a book that was written actually. So Doug Hofstadter, he's a cognitive scientist and also a physicist, and he wrote this book, Gödel, Escher, Bach, in Bach in German, but I think in the US people would call it Bach often, about the composer, and Escher, who is an artist who made these amazing drawings, and Gödel, one of the most famous mathematicians. And I stumbled upon the book when I was in high school, and it was written in 1979, and it's actually about a lot about artificial intelligence, cognition. It explains concepts such as recursion, logic, many of these things that are related to artificial intelligence and computer science, and it does it in a really fascinating way by coming up with these little stories around it and puzzles. And it's just, I was super excited reading this. I just did it by myself. And I actually didn't have the connection to other people where I could talk to them about it. But then at some point I asked someone, so when I came towards like deciding what I should study, I asked someone, so if I like that kind of stuff, what should I do? And that person said, oh, you should do computer science, because that's exactly about this kind of thinking, this algorithmic approach to problems. And yeah, that's how I got into computer science, and then AI, and ultimately robotics.
That's interesting.
So I honestly highly recommend people reading that book. It's really fascinating. I think even now, 79, so that's like 32 years old.
Yeah, it's like
40, no.
23 years. 23, yeah. Or 24, yeah.
44, no, 42.
42, okay. 42, okay, yeah.
Oh, no, wait. We are in 20.
No, 24.
Fifth, it's actually, yeah, 42. Okay, years old, and it's still super relevant. People
That's
should
very
take
interesting.
it. It's a fun read.
Yeah, thank you for sharing that. Thank you so much for sharing. Yeah, and lastly, I don't know, maybe the best advice was given to you, but it seemed this book was really a big impact to you. But if there's any advice was given to you and with the life is changing, and you would like to share with a student, an audience, I don't know, advice was given to you is life changing. Yeah.
Yeah, I think or advice, the way I say, I think what I learned is that people should maybe not, let's say, overthink their career or overthink their future. So I realized that often you should do things that you enjoy and that you are really excited about. And even maybe sometimes if in the moment it looks like, oh, that might not be the most supportive for your career, but you should still do what you think is good, right? And always be open to opportunities when something comes up, and you think that's a good thing to try. Just go for it, right? And then good things will happen.
I really like that. I think that's something, yeah, very, very powerful. But I think most people are afraid from risk. It comes down to risk. If you doesn't overthink and you want to foresee.
And you can't predict exactly what's going to happen, right? And
Yeah.
and you often can't predict what you're going to like 5 years in the future or so, or what you want to do, right? There's so many uncertainties. And again, if you're over planning, as you said, you're going to become also risk averse because you did all this planning and now you got to stick to it. And maybe that's not the best thing you can do.
I really like that. This is really, yeah, thoughtful advice. So I don't know if you have any final words you'd like to say for the audience. Any final words you'd like to say, if you have any?
I think I talked quite a bit.
As you like, if you
but
want.
Overall, yeah, I think robotics is just extremely exciting area, right? And it will have huge impact, and I think it has the potential to have hugely positive impact on our society. We are currently at a time with these new tools that we have, hardware, but also on the compute side, simulations, learning, and a better understanding of all these algorithms, that I think it's a super exciting time to be in robotics. And I encourage people to keep on working on that, and hopefully will really make this next generation of robots enable it.
Thanks so much, Professor Tito. I think that was really inspiring and such an honor again to have you. I really enjoyed it. Thank you.
Thank you so much for inviting me. It's been great.
Thank you.